For this segment, we're going to be going over the Mohr circle for strain. One thing that we didn't make clear last time is where we get this lambda value instead of our sigma value. So our lambda value is our quadratic elongation. This is going to be our elongation in either direction. So the basic formula for this is going to be our deformed length over our original length squared, or our 1 plus our elongation factor squared. So when we want to, we can combine this or break this up into our sigma or our lambda 1, lambda 3 components, which we use for our Mohr circle. Now, if we think back to our original Mohr stress diagram, we had our equations for sigma n and sigma s, right? Remember, sigma n was equal to our 1/2 sigma 1 plus sigma 3 plus 1/2 sigma 1 minus sigma 3 cosine of 2 theta. That was our final equation for sigma n. We got to this equation first by dissolving all of our vectors together onto one vector. We did this during class. So after we do that, we're going to derive how we got to this equation. So originally we have our sigma n, which we take our sigma 1, multiply it by cosine squared theta. Then we have our sigma 3 multiplied by our sine squared theta. Again, remember, this is taking angles, two different angles like this, combining them together so they are in one vector. We then substituted in these trig relationships, so cosine squared theta is equal to 1/2 1 plus cosine 2 theta, and sine squared theta is equal to 1/2 1 minus cosine 2 theta. So these are relationships that are already determined. We substitute these in for this in terms of our sigma n, and that's what gets us to this final equation that we use to calculate our normal shear. The same thing holds true for our sigma s. So remember from before, sigma s is equal to sigma 1 minus sigma 3 sine of theta times cosine of theta. This is the original equation that we were using. This is our vector quantity, trying to get it into one. We substitute in the following rule. So sine theta cosine theta is equal to 1/2 sine 2 theta. So our final equation for sigma s is 1/2 sigma 1 minus sigma 3 sine 2 theta. And this is the equation that we use for our shear stress. Now the reason that we're going over this, right, our sigma n and our sigma s, is that now that we're looking at our deformation, we're basically doing the same thing, we just have different terms for this. So we are going to have our lambda, which is going to be part of our Mohr stress circle, strain circle, and that's going to be our lambda 1 cosine squared of our trident plus lambda 3 sine squared of our trident. Now, we'll notice that if we go up to our normal stress, right? It's the exact same equation. We're just using different variables. So this is going to be, again, for our strain. And again, applying the same substitutions for our trig, we have our lambda, which is equal to our 1/2 lambda 1 plus lambda 3 plus 1/2 lambda 1 minus lambda 3 cosine 2 of our trident. So that is for the equivalent of our normal of our Mohr diagram. This is the equivalent. The equivalent of our shear is going to be our gamma figure, which is going to be our lambda 1 divided by lambda 3 minus lambda 3 divided by lambda 1 minus 2. Take the square root of that and multiply all that by cosine rho sine trident. Putting in our relationships, right, now our gamma equals negative 1/2 gamma 1 minus gamma 3 sine 2 theta, or it's 2 rho, sorry. And if we look up at our shear, it's very similar. The only difference now is that we have our negative sign, which we'll be using to plot up our Mohr circle for strain. So this is our final one for lambda. This is our final one for gamma. And we use that to plot up our circle.